last Friday I left off with this challenge to introduce recursion where you have to print a countdown, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. But you're not allowed to use any loops, and you're not allowed to cheat by hard coding print 10, print 9, print, et cetera, et cetera. And so what does that leave you with? All right, the only thing that you have left is functions. Oops, we're going to have to let's make sure that the audio is working here. All right, yeah, there we go. All right, so while that reloads, the only thing that you have left is functions, right? So I don't know how to do that immediately, but we can do it a little bit, right? What if I were to write a function that given n, an integer n, check to see is that at 0, so we'll print blast off, or is it at above the 0, and so we'll print out the actual number. Let me go ahead and erase that. We'll come back to the book stuff later on. Let's go ahead and increase the size. Is that good for everybody back there? Okay. So let me go ahead and create this function, int. Actually, we'll make it a void function first of all. And I'll call it countdown. And it'll take an integer n, right? And I don't know how to count down yet, but if n is 0, then what I could do is I could say printf blast off, right? Now I could cheat down here and simply just call this function over and over again on 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, because the alternative here will be to print the %d, the value of the integer, and then return, right? So I could call this function 10 times plus 1, so 11 times with fixed values. Again, that's cheating, right? What if I were to call this function just right now on that one value though, printf, or not printf, but countdown on 10. All right, so what is this going to print? Oops, GCC demo, just as it is right now. Oops, I screwed up somewhere. What's wrong? Oh, there we go. I swear I typed it correctly, but whatever. It's going to just print 10, right? That's because we made one function call on one value, n being 10, and it was not equal to 0, so it ended up printing out just the value. Well, I've got a function here that will print out a value unless it's at 0, in which case it'll print blast off, right? What's to prevent me from calling this function down here after I've already printed out the value? We'll call countdown again, but not on n, right? Instead on n minus 1, because if it's 10, I'm going to call this function again on 9. Then it's going to be printing out 9, and then it's going to call the function again on 8, 7, 6, 5, 4, 3, 2, 1, until you get down to 0, at which point it will print blast off. So we've successfully created a program here that doesn't have any loops, right? It has an implicit loop here, but it doesn't have any explicit loops. It only used a function to count down from 10 to 0 and blast off. That's called recursion, when you've got a function that calls itself one or more times, right? You've probably seen recursion before in mathematics, right? So here's the old joke. Let's just go to Google, not Goodreads, but Google. Google's got a little built-in joke here that if you ask it what is recursion, right? It'll try to correct you. Did you mean recursion? Yes, I did. Click on that. Did you mean recursion? Click on that again. Did you mean recursion? So what are we doing here? We're stuck in a loop, right? We're going back and forth on the same thing over and over again. You've probably seen it in mathematics, right? Mandelbrot set. Right? So there's not this nice fractal art that you can look at and buy and play around with, right? These are self-similar mathematical objects. One much easier way to look at this is the Sierpinski triangle, however you spell it. There we go, Sierpinski triangle, right? So here's one way of building the Sierpinski triangle. What you do, come on, I want that one. You start out with a triangle, and then you remove the middle fourth of it as a triangle. Then you repeat that over and over again on the 3 remaining triangles, 3 remaining triangles, 3 remaining triangles, and that gives you a basic two-dimensional, dimension gets all fuzzy when you're talking about objects like this. Fractal dimension is what you start talking about. Because whereas the original triangle here had dimension 2, this now has dimension slightly less than that, but greater than dimension 1, right? A line would have dimension 1. This can have a fraction of a dimension. And so the notion of dimension, when you're talking about something like this, it goes out the window and you need something else. We're not going to get into that. Instead, we're going to start talking about recursion as far as code goes, right? So again, in general, recursion is something that references itself. Right? That could be fractals, right? That could be other mathematical notations. For example, one that you've probably seen before that we're going to work with here is the Fibonacci sequence, right? So, oops, come on, over there. There we go. So this is defined recursively. If n is 1, then the value is 1. If n is 2, then the value is 1 as well. Otherwise, the value is equal to the 2 previous values in the sequence. So we're going to build this first few elements in the sequence here. Let me start out with 1 and 1, right? Those are the first 2 because those are called what are called base cases, and we'll define that more formally here in a second. What is the next one in the sequence? Well, it's the 2 previous values added together. So it'll end up being 2. Right? So what's the next one after that? Well, the 2 previous values in the sequence are 1 and 2. You add those together and you get 3. Right? Looks like you're counting, but you're actually not, because now here's where it starts to blow up. 2 plus 3 is going to be 5. Then we have 8, 13, 21, 34, 55, 89, etc. Right? It goes on ad infinitum, right? Infinitely. L dots. There we go. Right? So it's an infinite sequence, okay? And also it grows exponentially. If you've ever heard of the golden ratio, 1.6 something, 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 that's where it comes from. If you were to solve this thing, this is a linear homogeneous recurrence relation of degree 2. And you can actually find a closed form solution of this involving the golden ratio, which is about 1.61 something, something, something. Right? If you ever see the spiral thing, that's where that comes from. Right? So, but in code, when we reference code, that is, oops, not so, there we go. In code, a function is recursive if it makes one or more calls to itself. Let me give myself some more room here, okay? All right, so we have that over here in our countdown. This function calls itself. Now, we can go ahead and visualize this. Let's go ahead and do the Python tutor for the C and check and see what's going on here. Because there is a loop going on here. It's just that you don't see the loop in the actual code. Instead, you see, hopefully it works. Come on, do I have anything in there that I shouldn't? Yep, they're good, good. I'll go ahead and then zoom in here. Now, when you call countdown, what happens? A new stack frame is created with that particular value, 10. Well, that's going to be less, not 0, so it's going to end up printing that value out and then calling another function, the same function, on a new value 9. And so a new stack frame is created with that new value 9, right? And for every value in that sequence, what ends up happening is that you create a stack frame for each one. Right? So basically what you're doing here is you're doing the same thing that a loop would do, counting from 10 down to 0, but you're abusing the call stack to do it. Right? Now what if I wanted to do, and when it's done, of course, what happens? All of those stack frames start popping off the top until we get back to the original, right? So basically, we kept track of that index variable that we normally would in a for loop for int I, right? And then we had 10 values of them, 10 different values in 10 different stack frames. Immediately, that sounds kind of fishy because why would you need 10 variables when one will do, right? So let's talk about that. Let's talk about the good and the bad of recursion after we've talked about the designing of recursive functions, right? So there's a loop there, right? And remember, every loop has an initial condition, a continuation condition, or a terminating condition. That's when you don't do the loop anymore. And then you have to make progress towards that terminating condition. A recursive function has exactly the same thing. Every recursive function needs one or more base cases, in other words, a termination condition, where no recursion is performed anymore. What if you don't have that? Let me come back over here. What if I didn't have this base case right here? Right, let me go ahead and get rid of all of that and all of that. What's going to end up happening here? Do you see this? get rid of that, get it out of the way. All right. Predict what's going to happen here. I'm going to call countdown on 10. Then it's going to print that out. Call it 9, 8, 7, 6, 5, 4, 3, 2, 1. When I get down to 0, I no longer have a base case. So what happens?
Infinite loop, like.
Yep. Keeps going down, right? Infinite loop. Now, it will die here very, very quickly. Why? Stack frame on top of stack frame on top of stack frame. 261,839 or so stack frames. What eventually happens to your stack? Overflows, right? And that's where I get my segmentation fault here. So if I don't have a base case, I have a runaway recursion. In fact, even if I didn't have, what if I wanted to count down from 1 million down to 0? Would I be able to do it recursively at all? Oh, really? All right, let's try it. So I'll go ahead and restore everything. Right, there we go. And I'll start at 1 million. Is that 1 million? That's 10 million. Oh, let's just go ahead to 1 million here. All right, GC, see this? Remember, I'm going to hit that stack overflow. What's going to happen? I only was able to get down to 738,045. Right? So even deep recursion, even though this is not a infinite loop here, it still is a deep recursion. I can only make 261,000 function calls. Right? So even if you don't have that problem, you still have the problem of abusing your call stack there. Some cases may be error handling. Let me actually indent that because it's part of the same one. For example, what if I said, okay, well, what if I started out negative, right? No, my countdown is going to go from 10 down to 0. So if you start me at negative 10, no, I'm not going to allow that. I'm going to go ahead. In fact, what would happen here? What if I started out at negative 10, right? GCC this and run it. I'm past my base case already. So what I'm going to do is I'm going to add another error handling base case. If n is less than 0, what I'll do is I'll say return immediately. Don't do anything. Right? Else if. Right? There we go. Now, I would agree that I could probably count down from 1 million if I redefine the call stack to have a lot more space, but I'm not going to mess with the call stack right now, the size of the call stack. All right? So now what happens here is basic error handling, that nothing will happen because you've started past your breakpoint, your base condition, and so it just simply returns. Right? So some of those base cases could just be simply for error handling. Right? Finally, you make one or more recursive calls that must make progress towards that base condition. For example, this is a countdown. What if instead I had counted up? Would I ever actually reach 0? Nope. So let's go ahead and go down to 10 here, GCC this, and instead I'm going to have an infinite loop the other way. Right? I'm not making progress towards my terminating condition. Eventually I will hit a stack overflow here and a segmentation fault. Right? So you need to make progress toward, by decrementing or incrementing or doing whatever you're doing. In other words, you've got a termination condition, you've got a progress towards that termination condition, I++, I minus, and then finally you have an initialization. Right? You have to make the initial call to a recursive function. And we won't do this, but oftentimes, function. What you'll do is you'll have a main entry point. You'll have a non-recursive function that then that you call, and then that calls a recursive function that kicks off the recursion, right? And so this is countdown main would call the countdown recursive or something like that. We're not going to get into that, and instead we might do that later if you ever take CS2 or 3 or something like that, but we won't get into that just now. Understand, though, that these 1, 2, and 3 conditions, that's exactly what a loop is. You have an initialization, you have a starting point, you have a continuation or a termination condition, and then you have to make progress towards that termination condition. Otherwise, you have an infinite loop, and you have infinite recursion. So why are we even covering recursion? There are some good things about it, right? Recursion can be useful or good, right? For example, many divide and conquer and home row today, conquer algorithms are presented recursively. Merge sort, quick sort, binary search, these are some things that we're going to look at later. basically, I don't know how to solve this problem, but this problem with 10 things, but I can go ahead and divide it into 5 things, and that's a little bit more reasonable. I can handle that smaller problem, maybe. I still don't know how to do it. So let's go ahead and cut it in half again. And okay, 2 things, maybe that's doable, maybe that's not. Cut it in half again. 1 thing, I can deal with 1 thing, right? So I've divided it, now I'm gonna conquer that 1 thing and then put these 10 things back together for a full solution. That's a divide and conquer kind of strategy. Next semester, you'll probably be taking 235. In 235, you look at various proof techniques, and one of them is induction. So you want to prove this statement holds for all integers. Well, what you can do is you can start at the first integer. It holds for 0. Right? And then what you can do is you can start at an arbitrary location I. And you can say, well, let's assume that it holds for I, and that we'll use that assumption to prove that it also holds for I plus 1. Since you had a base case, it holds for all integers, right? Because I need to show that it holds for 55. Okay, well, just prove that it holds for 51 because the previous proof showed that I implies I plus 1. And I'll just work your way back all the way to 0, right? That's recursion. It's thinking inductively, right? In fact, in some languages, it's necessary. Haskell, Scheme, Lisp. These are called functional programming languages that you'll probably eventually see, but probably not use in your daily lives. And basically they are more functional style, and they don't have, in fact, Haskell does not have variables that you can set. Int x is equal to 42. You can't do something like that. There are no variables. There are no loops, or loops are highly discouraged in those languages. Even Python, right? If you're coming from a Python background and you find yourself doing a traditional for loop for I in range, right? You're not doing it the Pythonic way. You should be doing it using list comprehensions and functional programming style. That's the Pythonic way is what they call that. So it is useful in a lot of languages. In fact, it's necessary in a lot of languages to think like that. And finally, recursion can also lead to simple, clean, beautiful code that is easily understood. I don't know. This. I've got what, a dozen lines here or something like that, just to simply do a countdown. Is that simpler than a for loop? Yes, no, I don't know, right? Is it cleaner than a for loop? Is it more beautiful than a for loop, right? Those things are all subjective. In fact, everything I mentioned here is absolutely subjective, right? The bad, however, is completely objective, right? So what are the bad parts of recursion? Well, we've already seen one of them. You risk overflowing your stack with a runaway recursion. I couldn't even count up to 1 million using recursion, right? With a count down or count up, whatever, because I would eventually overflow my stack, right? Even if it isn't a runaway infinite recursion, you're still abusing the call stack. It is small, it is defenseless, it is limited. Don't abuse the call stack, right? Instead, rewrite it as a traditional loop. In fact, there are some organizations, NASA being one of them, that forbids its coders from using recursion because of this risk. And because you're working in embedded systems where your stack is no longer 4 megabytes, now your stack is literally kilobytes. And you cannot afford a stack overflow at all. Right? Most or all recursion can actually be rewritten as a regular old loop, or you can simulate the recursion using a stack, right, an in-memory stack. In fact, we'll eventually look at quicksort, qsort in C, and sort in Java. Java, it is recursive, but only down to a point, and then it switches over because the recursion is so expensive. And in C, usually it's not a recursive implementation. Instead, it simulates recursion, right? Because they realize that recursion is actually very expensive, or can be very expensive. And finally, you also risk exponential blow up to a problem. Now for this, I want to go back to our Fibonacci here. I have 2 copies. I shouldn't have 2 copies. We don't need 2 copies. There we go. Get back to 1. All right. Anytime you see recursion, or anytime a recursion is introduced, if you've already seen recursion, please confirm this or not, they will always go to the Fibonacci sequence. So the first time you saw a recursion, you probably saw a Fibonacci sequence, right? I hate it because it's a terrible example, right? Because Who cares about the Fibonacci sequence? Like I said, it's a linear homogeneous recurrence relation of degree 2. There are an infinite number of those, right? Ooh, it leads to the golden ratio. No, it's not. It's nothing mystical or special about it, right? I like it because it is a terrible example. It's a terrible example because it shows you exactly the pitfalls of recursion. Let's come over here and implement the Fibonacci sequence in code, right? Now, I'm not going to use integers. I'm going to use longs because it's going to be it's going to blow up, right? And so a long is a 64-bit integer, and it can represent up to 2 to the 64th. Let's go Wolfram Alpha here, and nope, come on. Wow, it's slow today. Why? Wolfram Alpha. It can represent numbers up to, come on, 2 to the 63 minus 1. Come on, 2 to the 63 minus 1. There we go. Whatever that happens to be, quintillions or something like that. Yeah, 9 quintillion, right? We're going to be able to express larger and larger Fibonacci numbers. Fibonacci. There we go. That's how you spell it. Right? And we're going to take as input n here. Right? Now, I'm just going to simply transcribe the mathematical definition here. If n is 1 or if n is 2, I will return 1. So if n is 1 or n is 2, I will return 1. Now you can go back and if it's not defined if n is less than 1. Some folks define it starting at 0, then 1, 2, 3, etc. I'm going to go ahead and start it defining at 1. But if it's less than that, if n is less than 1, then it's undefined. We can return some sort of flag value here, -1, to indicate that that's undefined, right? Else if. There we go. Right? Else. Now it's not one of those base cases. So again, all I'm going to do is transcribe this over here. Fibonacci of n minus 1 plus Fibonacci of n minus 2. Right? Fibonacci of n minus 1 plus Fibonacci of n minus 2. There. And let's go ahead and return that. Okay. Now down here, let's go ahead and read this in as a command line argument if you want to. Int n is equal to arg v, or a to I of arg v sub, I don't know, 1. There we go. So I'll read this in as a command line argument. I'll leave you to do the basic error handling there. And then I'll go ahead and create a long here. Result is equal to Fibonacci of n. And then I'll print it all out. So Fibonacci fib of %d is equal to, the placeholder for a long is I think LD. Maybe it's LLD. I think that this is good enough though. We'll find out. The compiler will tell us. And result. Okay. GCC. There we go. We're good. Maybe I should use GCC with the wall flag there. Yeah, we're still good. All right, so let's go ahead and run this for, I don't know, 10. Right? 55. Is that correct? Well, let's come back over here. We did it by hand, right? This is a perfect test case because we did it by hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 55. What if I called this on 11 instead? What would I expect then? It was 89? Okay. We didn't write it down, but what if I called this on 12? So 55 plus 89 is 144? Yeah, I got it. Cool. I can do it in my head, yay. Right. Let's do this for 65. How long should I wait here? All right, well, let's do some calculations while we wait, right? So Wolfram Alpha can do this quickly. Fibonacci of 65. I think we're going to be off by 1 here because they started at 0, but that's okay. Whatever the 65th Fibonacci number is, we'll be off by 1. Come on. Wow, you are slow today. All right, there we go. It's a big number, 10 to the 13th, right? Now, what if I did, I don't know, 1 million calculations per second there, right? Right? That's 1 second of calculations. Seconds to, I don't know, days? Let's find out how many days that is. That's 198 days. So it's a little over a half a year to be able to wait for this. And that's at 1 million. What if I gave you an even more powerful computer here? I don't know, 1 million operations per second, 1, 2, 3, 1 billion operations per second, because that sounds more like a modern computer. That's still going to take a good chunk of an hour, right? 0.2 days, what's that going to be? 0.2, that's going to be several hours? I don't know, hours. Let's just move it to hours. Yeah, it's going to take like almost 5 hours there, right? And I don't think actually that that this virtual instance over here is actually that powerful, 1 billion operations per second. We can go ahead and make some estimates, and you'll do that in your lab and hack, but no way is this going to execute here. To understand why, let's visualize it, okay? And to understand why my estimate was okay. When you call Fibonacci of 5, what happens? 2 function calls are made. One to Fibonacci of 5 minus 1, 4, and one to Fibonacci of 5 minus 2, which is 3. When you call Fibonacci of 4, it makes 2 calls to 3 and 2. When you call Fibonacci of 3, it makes calls to 2 and 1, etc., etc. In other words, you have this big tree, and that's only for 5. Now think about 65, right? 65 is going to call 64 and 63. 64 is going to call 63 and 62 and the other side there, right? It's going to be huge. How big is that tree going to be? To understand that, all you need to do is start counting up the number of leaves here, right? Or not the leaves, but the number of nodes for each one. So just as an estimate here, Fibonacci of 5, right? How many times is that called over there? 1, right? Just at the top, right? So how many function calls represent that thing right there? 1. How about Fibonacci of 4? How many Fibonacci of 4s do you see in this diagram? Just 1, right? Right there. Not a trick question. All right. So just 1 over there. All right. Fibonacci of 3. How many do you see in this diagram here? I see 1 right there and 1 right there. Right, so there are 2 of them. Right, 2. Do you start to see a pattern? Fibonacci of 2, how many times is that called? I see 1, 2, 3. Right? So 3. Hopefully now you start seeing the pattern. How many times is Fibonacci of 1 called without even counting them up? 5. Right, now let's go count them up. Fibonacci of 1, there's 1, 2, 3, 4, 5. Right? And then it falls apart on 0. 0 is only 1, 2, 3. That's a little bit different. But why were you able to predict 5? What is this? This is the Fibonacci sequence. The number of function calls is going to be equal to the number of, or to the actual value of Fibonacci. So let's come back over here to Wolfram Alpha and ask, what was it again? That, right? Fibonacci of 65 is going to make that many function calls. Right? Well, first of all, we would never, actually we would get down to that depth, but that's going to be 18 trillion, it looks like, or something, nearly 17 trillion. 17 trillion function calls. That would be like trying to compute 1 plus 1 plus 1 plus 1 plus 1 17 trillion times. Why are you doing it like that, right? Just give me the number, 17 trillion, right? So this is not at all acceptable. And it demonstrates that you have an exponential solution to this problem. Right? Now, everybody in here could probably write a for loop to do this, right? All you need to do is keep track of 2 values. Just initialize it to 1 and 1. Now you need a temporary variable here, c. And c is going to be the 2 previous values added together. Then move your 2 previous values over, and so you only need actually 3 variables. 2 variables and then a temporary variable, right? Do we want to do that really quick? No? Okay. Because what I want to do is I want to show you other more sophisticated ways of avoiding recursion. Right? Okay. Eliminating recursion. You can always rewrite a recursive function using a regular old loop, right? Old loop. For loops, for example, right? We won't do that because you didn't want to, right? You can always simulate simulate recursion using an in-memory stack. Right? In other words, don't abuse the call stack, LIFO order, last in, first out. Instead, create your own array and then treat it like a stack. And pushing something just means adding something to the end of the array. Popping something just simply means removing the last thing in the array. Right? And you can simulate it. There's something called tail recursion. In fact, that's probably the easiest way to eliminate recursion, because what it does is it doesn't use stack frame on top of stack frame on top of stack frame. The compiler can actually compile away your recursive code if you design it so that it can do that. Again, we won't get into that. Instead, what I want to do is I want to show you another technique entirely called memoization. That is not a misspelling. It is not a mispronunciation. It is a weird word that was created because they thought they needed a new word to represent it, something new, and right? It's actually not something new, right? It's called caching, right? Also called caching, right? So what is caching? Once you compute something, you save it, you cache it away, so that next time you need to compute it, you don't recompute it. You look at the cache and say, oh, okay, well, there it is, right? I can reuse that value. And it works as follows. Go ahead and use recursion, but, ... The basic steps are if you, once a value is computed, store it in a table or tableau, right? And the next time you need it, don't recompute it. Instead, use the value stored in the table. Right? And you do this trick all the time. Anytime I'm using an API where they limit you to, like, you can call this API, but you can only call it 10 times, and then we start charging you. All right? Or 10 times a minute or something like that. Okay, fine, I'm not going to do that. I'm going to call it 10 times a minute, and if I need a value again, I'm going to store it off into a database or store it off into memory or store it somewhere so I don't have to pay for that API call anymore, right? Because even if they're not charging you, API calls over the network, that's extremely expensive, right? Networking is always going to be a bottleneck, okay? What we're going to do here is we're not going to recompute it. Instead, we're not going to recompute, Fibonacci of 2 5 times. We're going to compute it once and store it in a table. Anytime that you want that value, we're just going to go to the table to grab it. Right? All right, so here are the basic steps. Basic steps. We're going to maintain a table full of values. Right? We're going to initialize the table with the base cases. Then we'll call a recursive function passing in the table. Right? If the table contains a value, we use it. Otherwise, ... we pay for the recursion and compute the value, but then store the value for future use. Okay? We've computed it once. I don't want to compute it again. I'm going to store it in a table. Now, let's actually do this solution for the Fibonacci sequence. Okay? All right, let's come over here. Well, I want a table full of longs, right? So before this, let's go ahead and create a table of long values here. Long start, values, let's say, is equal to a call to malloc, long star malloc, right? And size of long, right, times. Now, how many of them are you going to need? I want to compute the nth Fibonacci number. It is undefined for 0. So if I look at this as index 0, 1, 2, 3, ... n, that's undefined. I'm going to just leave that blank. Right? I'm going to burn that value right there. 1 and 2 are going to be 1 and 1, ... This is the value that I'm interested in here. So how big of an array do I need to store all these things if I don't want to have to minus 1? Right? N plus 1. So n plus 1. Then I'm going to initialize all the values, right, with a flag value to indicate not computed. For int I equals 0, I is less than n, I plus plus. Actually n plus 1, right? Because the size of our array is n plus 1, right? Now what value could I put into that table to say, this has not yet been computed? Something like this, right? What kind of flag value could I use? Negative 1, all right. So value z sub I is equal to negative 1, because that will never appear in the sequence. I could also use 0 if you want to, right? But I'll go ahead and use negative 1, okay? Now I will initialize the base cases. So value sub 1 is equal to 1, and value sub 2 is equal to 1. So I'm working backwards. There's my base cases. I established those first. Right? And then I'm going to call Fibonacci of n and pass in the values. Right? I don't need to pass in the size because I will assume that the size is big enough to accommodate this thing over here. Okay? Let's modify this. Long star values. All right, so if it's outside the range, fine, that's my base case. If it's 1 or 2, then I can return 1, that's fine, right? Otherwise, I start checking. Is it already computed, right? So if values of n is not equal to negative 1, my flag value, that means I've already computed it, right? It's already in the table. So what value should I return? Whatever value was stored in the table. Right? So if it's already computed, just use it. Right? And there it is. Otherwise, it's not yet been computed. Not yet computed. Pay for it. ... All right? So there we go. I'm not going to return it though. What I'm going to do is I'm going to store it into a value. Long x is equal to Fibonacci of n minus 1, Fibonacci of n minus 2, passing in the values. Passing in the values. Now, once I've computed it, I cache it. And I say value sub n is no longer equal to my negative 1 flag value. Instead, now it's equal to x. Okay? Let's see if this compiles or if I screwed something else up. Okay. Sorry. Yeah. Then return it. All right. X. There we go. Return x. Thank you for saving me from myself there. Okay. All right, let's do it again. Well, first of all, let's do some regression testing here. Did I break anything, right? The value of 10 should have been 55, right? Okay, I didn't break anything. The value of 11 should be, what was it, 89? Didn't break anything. 144, didn't break anything. But now let's go ahead and try that very large value there, 65. Came back immediately. Right. Why? Well, I don't have it over there anymore. Oh, whoa, I don't know what I just did there. But, oh, come on. All right. I touched it somehow. Okay, how do I restore that? No, I think I just zoomed in. How do I reset it? There we go. Okay, and then I'll zoom back out there. It was like a 3-finger touch zoom on the Mac that I screwed up. Anyway, it came back almost instantaneously. Now think about this with respect to the tree. We had this big, giant tree that was exponentially sized. One with 17 trillion little leaves and nodes here. But what we did with memoization was we never went down this path because it would have been computed over here, right? Once. So that cut out this entire half of this tree. It's like having this big giant tree and then you cut half of it off, all of its branches. Well, that's not it, right? That's not all, right? Down here, when we go over here, this would have been cut off as well, this big giant part over here. And then this big giant part would have been cut off until all you were left with is this one trunk, basically. Right? Imagine a tree that you've cut off all the branches. Right? And now it's just a trunk going up to the, I mean, it's going to die, and you don't want to do that to a real tree. But a computation tree, yeah, you want to do that. Right? Because instead of coming back 5 hours later, I've got my answer instantaneously. Right? That's memoization, and that's the power of caching things. We only have 10 minutes left. Can we do the same thing, but more sophisticated over here in Java? We're still limited by, if I used a long, we'd still be limited by that 2 to the 63rd minus 1, right? I don't want to limit myself. I want to use what's called a big integer. Right? A big integer is going to be, it's an arbitrary precision integer. It can be as big as you want. When you reach the limit, it allocates more memory so that you can fit more decimals, more digits in it, right? And unfortunately, you can't do regular old math with it. But I can call Fibonacci on it, on n, and something else, right? We're going to, so I need to actually write this. So public static big integer, Fibonacci of int n, right? And I could steal a lot of the, yeah, I do need to import this. It's in the java.math library. There we go. And I'm going to steal most of this code here and adapt it. There we go. It is so slow. I don't know why. Anyway, if it's less than 1, I'm not going to return a flag value here. What I'll do is I'll throw an illegal argument exception. Exception. There we go. Fibonacci is not defined for n equals plus n. Right? And we can go ahead and, I misspelled it.
You forgot the new keyword.
Oh, thank you. There we go. All right. That's how you do proper error handling in Java. Don't return, don't exit, right? Just throw an illegal, throw a runtime exception or something. Right? Otherwise, if it's 1 or 2, we'll return the big integer version of 1. Right? Okay? Otherwise, we'll come into this. Now, values of n. I could use a list or I could use an array, but I want to use something more sophisticated because this is good old Java. Yeah?
We use a hash set.
A hash set, that would store values, but how do I have an input? Like I want 10 maps to 55, right? So I could store 55 with the hash map. There we go. So public static map of integer mapping to big integer, right? And integer values, we'll say, is equal to new hash map. Right. Now what this is going to do is this is going to map maps n to Fibonacci of n. Right? And now you understand what a map is. It's a function. Right? It maps things in a domain to things in a range, a codomain. Right? I have to bring all this stuff in. Come on. Import. This is not my regular demo code that I've already imported everything that I'll ever need into it. And import. There we go. All right. Now I do need to initialize those. So initialize with base cases. And so normally what I would do is I'd say values.put 1 maps to 1 and 2 maps to 1, except that I can't use 1. I have to use big integer dot 1, right? And big integer dot 1. Right? And I can't just do it willy-nilly anywhere I want. Right? Let me show you something new, or maybe it's not new. Static variables are initialized, like this new hash map here, when the class gets loaded up by the virtual machine. You can also put what's called a static block here. Right? That is function, that is code that's not in any particular function. Instead, it's in a static block. That will get executed when the class gets loaded up by the Java virtual machine. Right? Often people will put that kind of code into an init function, initialize function, or you can put it here in a static block. Right? Okay. Now, what I do to ask is ask whether or not that value has been computed. Right? Values dot contains key. Do you contain the key for n? Right? And if that's the case, then I can use it. Return values.get n. Right. There we go. And we've got 5 minutes. Wow, we're cooking along here. We're doing well. Otherwise, you've not yet computed it. So I will go ahead and compute and pay for the recursion. Right? Pay for the recursion. The difference here, though, is that I cannot use plus here. What I have to do is this returns a big integer, and so I can say dot add Fibonacci of n minus 2, and that's equivalent to the addition. And this is going to be a big integer. There. Okay. Now cache it. Values.put n is going to map to x. And then finally return it. All right. Now we're all good. Let's go ahead and run this. I've got it set up for 10 here. It should be 55 if all goes well. Run it. There you go. Oh, sorry, I'm not printing it. Result. I'm going to go ahead and print it as a string because it's not an int that you can print out with %d. Instead, it'll output a string representation of it. 55. All right, let's increase this. 11. What was it again? 89. Okay. 12. 144 when it gets done. Now let's go with up to 65. Remember, it's going to be that 17 quadrillion or trillion or whatever it was. Hey, that looks familiar. But guess what? Let's go in 100 here. 200? Oh, 200, not 1200. Save that. Run it. I can go as big as you want. Right? That is way more than 2 to the 63rd. Right? I don't know. Let's try 1,000. I think that this will work. I'm not sure. We might run out of memory here. Nope, we didn't run out of memory. Right? So wow, that's a huge number, isn't it? Right? I can represent that with a big integer because if it gets too big, we don't have overflow. It allocates more memory and to represent that number. 1 million would be too much for the recursion, so 10,000. I think we can do that. Okay, there we go. I finally hit my limit here. I didn't hit the limit of big integer. What limit did I hit? The stack. Right? Trying to go down 10,000 layers in the recursion, right? Yes, you've cut off half of this tree here, but still, this is way too deep for the recursion. Right? Might as well go with a for loop, right? You're still hitting the main problem of recursion is that you risk deep deep recursions risk stack overflows. Right? So 10,000, we got to 260,000 with C. We only got 10,000 or whatever it is. We didn't even get to 10,000 here in Java. Right? Okay. So what would be your ultimate solution here? Eliminate memoization too. Right? Your ultimate solution here would just be a for loop in which you're computing previous values, or you can fill up this table. It's just that you're gonna risk stack overflow there. Good. All right. Remember, maps are your friends. Right? Maps can do a lot of stuff. You can map anything to anything, and they're my go-to data structure if I'm going to do anything. Right? Okay. All right. So we're done with recursion. What we're going to do for the rest of the semester, starting on Wednesday, is we're going to go through searching and sorting. If you've not already looked ahead, the Monday and the Tuesday, we've just called it. There's no lecture. There's no lab next week. So you've got the entire week of Thanksgiving to yourself. And then we'll come back. There's 2 weeks after that, and then the finals week. Make sure that you're doing the PDC modules before you go off to break. You don't have to do them before break. We recommend that you do that just to get it off your plate. When you come back from break on the 13th, that's when the post surveys are due. So you'll go through the same surveys that you did at the beginning of the semester that hopefully you don't remember them. But the idea is that if you've gone through our PDC modules, then you've increased your knowledge to the point where you're going to answer those questions a lot better, right? And we're going to measure that improvement. Okay. Otherwise, we've got help hours here in a moment, and I'll see you on Wednesday.